onto Newton's second law, it's often directly misquoted as being that force equals mass times acceleration. However, the actual second law isn't that. This force equals mass times acceleration, this formula here, is actually called the special case. And Newton's second law overall is known as the general case. So the general case, if we read from here, it says that the resultant force is proportional to the change in momentum per unit time. Now, we haven't got onto momentum just yet, but momentum is the product of mass and velocity. So say this is momentum at the final stage, and your initial momentum is m times u. Force is therefore proportional to mv minus mu over t, or delta t even. I leave it just as t because we usually take our velocities at time equals t, or time t equals 0 and time t equals t, so delta t therefore equals t in that case. But how do we get from the general case, therefore, to the special case? Well, here's the proof. So we start with the general case that we know, proportional to mv minus mu over t. We can factor an m out from the numerator, so we get m times v minus u over t. To get this, we should recognize that, excuse me, v is u plus at. So v minus u is at, so a is v minus u over t, which we can substitute in here. So force is proportional to mass times acceleration. So force is some constant k, so k is constant, or a constant rather. However, we have defined 1 Newton as the force required to accelerate a 1 kilogram object from rest to a speed, I should say, so that should be 1 meter per second. It could be at an acceleration 1 meter per second squared to a speed of a meter per second, but that's a bit complicated. So it's the force required to accelerate a 1 kilogram object from rest to 1 meter per second. So 1 Newton is k times 1 kilogram at 1 meter per second squared, so k is 1. And so there F is equal to ma. So now you know how to derive one of the most famous equations in physics.